Hello guys, today we will talk about the structure 1.1.3, kinetic energy and temperature. As I mentioned before in some videos, I'm a full-time chemistry teacher in an international school. I have more than 8 years of experience as a chemistry examiner. I could say that I have more than 8 years teaching the IB. Okay, so the structure of this video is that I will talk about the learning objective, about 1.1.3 specifically in this part of the syllabus. We'll do the explanation of the topic using different resources, and I will be writing, and then we will have the opportunity to practice past paper and exercises about this topic. Structure 1.1.3, kinetic energy and temperature, has learning objective. It says that the temperature in Kelvin is a measure of average kinetic energy of particles. So in that case, you will need to interpret observable change in physical properties and temperature during changes of states. And you will need to compare between values in the Celsius and Kelvin scales, how to transfer from one scale to another one. It will be very straightforward. So we have here, so it says temperature is constant during a change of state. This diagram is very important because it allows us to visualize what is happening with the temperature and the relationship with the energy. In that case, we see that in the y-axis we have temperature, in the x-axis we have energy input, different than kinetic energy, and I will explain you what. If you see in this diagram, we have the states of matter. Here we have the solid, liquid, and gas. Yes. In videos before, we talked about the solid structure, which are packed structures. Then we have the liquids with the molecules or compounds are attracted by intermolecular forces. And we will see that in gases, the molecules are spread out, the forces in gas. In this diagram, we will analyze the changes in the microscopic level, and then we understand the macroscopic. So when you see there is an energy output from A and B, it means that this is the solid state. In this case, we could say increasing the temperature. We are increasing the movement of the particle because it's a solid. We are increasing the vibration of the solid. But there is one moment when this solid is broken, and then the structure won't be as it was before. So this is what happened when the molecules start to vibrate. So the temperature is increasing, kinetic energy is increasing. Here, even though it's an energy input, the temperature is not changing. And we said, what is not changing? So we say that in B and C. This is the melting point, this line over here. So the vibrations are sufficiently energetic for the particles to move away from their fixed positions and form a liquid. They are forming a liquid in this transition state, in this melting point. During this stage, so if you see the energy input is still increasing in the x-axis, is used to break the interparticle forces, not to raise the kinetic energy, so the temperature remains constant. If the kinetic energy is not increasing, it means that the temperature is not increasing. And this is very important. Temperature is only a measurement on the kinetic energy, and they are strictly related. We could say that if one increases, the other increases. If one is not increasing, the other is not increasing, as we can see here. What happened to the energy input? Because you see that the energy input is increasing. So I will highlight this in green so you have this idea very clear. The energy added during this stage is used to break the intermolecular particle forces. We are not increasing the kinetic energy of the molecule. This is what happened in B and C. Again, here we have from C to B, here we have another energy input, and the kinetic energy of the molecules is increasing as the temperature is increasing. You can see very easy in this graph, in this part from C to D. So this is increasing, but again, something happened here from D to E, a different color from E to E. And I will show you this just here. Here we have from D to E. If you see there is no increasing of the kinetic energy, it means that there is not increasing on the temperature, but the energy input is still increasing because we are talking about the x-axis. The energy input is still increasing, but what is happening to that energy? It's working on breaking the intermolecular forces in the liquid state. Let's see what is here. So in CD, let's recap what is happening here. CD, this is when we are increasing the temperature here. It says, as the liquid is heated, the particles gain kinetic energy, and so the temperature increases, something that I told you before. Is the changing is the boiling point, and in that boiling point is when the energy input is spent to break the intermolecular forces. This is what we have here. This is the boiling point. There is no sufficient energy to break all the intermolecular or the particle forces and form a gas. Note that this state change needs more energy than the melting, as all the interparticle forces must be broken. So in that case, there is another important idea, is the following. If you see this energy is different than this energy, the graph is illustrating that this is bigger if you compare the two sizes. Because why is bigger? Because it requires more energy input to break more intermolecular forces. In this case, we were breaking the packed solid structure. It's larger here, intermolecular forces. And this is when the liquid, the compound, the particle become a gas. So here we have solid to liquid, we have melting point, let's highlight it in blue, liquid to gas, this is the boiling point. Another very important idea here and is the term endothermic and exothermic. So this is mentioned in the IB textbooks, and it's important that you know this regarding this graph. Endothermic process, we can understand that endothermic process is when you are adding energy to the system, okay, from the surroundings, absorbing them to the system. If you see, always when you can transfer, when you can pass from solid to liquid, this is an endothermic process because you need energy in order to overcome the melting point, this state of change. So this is the energy required in the laboratory when you want and you need to add energy. You have to increase the heat of this solid substance, and then you will get hopefully the liquid. Okay, if you are talking about, you will have the liquid. But if you see, you introduce the energy, you were the one that were adding the energy. It happened the same from liquid to gas. If you want a liquid become a gas, you have to increase the energy. So you put the water, let's say you put water in the beaker, and then you put the Bunsen burner and you wait for 100 Celsius degrees or something similar, and then the liquid water will become gas. You are adding energy. So when you are putting the Bunsen burner, you are adding the energy. This is an endothermic process, and it's important that you have this in mind, that the other way around is exothermic process. When you have a gas and this gas becomes a liquid, we are talking about an exothermic process. Why? Because the molecules in the gas state are losing the energy. And when they pass to the liquid state, so this energy is released to the surroundings. This energy is released. So the molecules in the liquid, we could say like this because we have intermolecular forces. Remember that this is not a solid, there is movement in these molecules. These molecules in the liquid state are a little bit more packed than in the gas. So here the movement of the molecules and the kinetic energy was very fast compared to the liquid. That's why what happened to the energy from the gas to the liquid, the energy needs to go to one place. So the energy is leaving the system, a change of state, and is released into the surroundings. Is the same when you have the liquid and then you have the solid. So in that case, you have intermolecular forces which are weaker than the solid pack bonds of a solid. If you see, the movement of these particles was very fast compared to the solid. The energy is going to the surroundings. Then the change from liquid to solid, the solidification in this case, is releasing the energy, which is an exothermic process. And here this condensation will be also an exothermic process. So keep in mind this idea. Something important that I forgot to mention here is what happened from E to F, but here we are to clarify this part. And the thing is that as the heat under pressure, the kinetic energy on its particles continue to rise as does the temperature. So when you are increasing the energy output and under pressure, the kinetic energy, the movement of the gas particles is increasing. So that's the temperature. Okay. This is the final part of this diagram. The first part, the last part of this um, picture that is illustrating the energy input versus the temperature, and something that you have to understand clearly because the questions are about this. What we have here is the second part of the learning objective, and is the temperature in Kelvin and the temperature in Celsius. Okay, so temperature in Kelvin is known as the absolute temperature. As we know the absolute temperature, which is Kelvin, then we need to talk about absolute zero. Okay, so Kelvin is another scale that we use to talk about temperature. The thing is that in our macroscopic world, we can feel the temperature, but in the microscopic, when we see that a solid is hot and you touch this, what is happening in reality is that the molecules are vibrating. If it's very hot, it's because the atoms are vibrating very quickly. Okay, and if the surface is cold, means that the atoms are not vibrating a lot, but they are still vibrating. And this is what it comes to this idea. Absolute zero is the lowest possible temperature attainable, as this is the temperature at which all movement stops. Wow, this concept is very important and it's beautiful because that concept is the way that you use to identify the relationship between temperature and kinetic energy. Here we have water, and I here have the Celsius scale, and here I have Kelvin. So if you see, let's talk about Celsius because this is the one that we will use in our daily life. Zero will be temperature of water. So water zero. Okay, keep your eyes in the red one here. And 100 Celsius degrees, what happened is that water boils. Okay, let's keep in this Celsius part first. Now, once we have this Celsius, we have negative 273.15 here. This negative temperature is the one that in Celsius degrees there is no movement at all. If one solid is at there is still movement, but when the solid is in negative 73.15, in theory, there is no movement at all of the molecule. Yes, when the molecules start to move a little bit, the temperature will increase from solid to liquid and from liquid to gas state. Now that this is clear for us, then we are transfer this to the Kelvin scale, where water boils at 373. It will freeze 273.15, meaning that 0 Celsius degrees is exactly the same as 273.15. So transfer from to one scale of temperature to another scale of temperature will be very easy for you. And here the absolute zero is zero. And this is why the theory is telling us absolute zero, zero. That's beautiful and it makes sense because now absolute zero when there is no movement of particles in Kelvin scale. This is the Fahrenheit scale, and those are just the numbers for the Fahrenheit scale. The absolute zero would be negative 459.67 degrees. It will be 32, the freezing point of water, and then the boiling point will be, okay? But most importantly, we focus in Kelvin and Celsius. The relationship between the Celsius and Kelvin, and this is that the temperature increase of 1 Celsius is also an increase on 1 Kelvin. Okay, so if I have 25 Kelvin to 26 Kelvin is the same energy that 26 Celsius degrees to 27 Celsius degrees, it will be only one. Okay, so this is only one scale, one increase in another terms. Here we have, this is the one that we will use the most. Those are the ones, the most important ones. So if you need to find Kelvin and the Celsius degrees, I am using this one. So they say, for example, you have 25 Celsius degrees. What is the value in Kelvin? So you just need to, as this formula says, Kelvin equals 25 Celsius degrees plus 273.15. Okay, so Kelvin, then I will go to my calculator. That will be 25 plus 273.15. 98.15, and then we have 298.15 Kelvin. Okay, so by the way, this is room temperature, 25 Celsius degrees, and that will be room temperature in Kelvin. Another scale that you will use is this one, another formula. So we have, if you have, let's say, 244 Kelvin, and you want to know what is in Celsius degrees, you just use this one. 244 Kelvin minus 273.15, and then you have the Celsius. So let's do in our calculator. So we have 244 minus 273.10, and then you have negative 29.15. Okay, this is how we transfer from Kelvin to Celsius and from Celsius to Kelvin. So this is something very okay. What we have here are some exercises, some problems that you would face. So these are not past paper questions, but these are very familiar and very similar to the ones that you will find. The thing is that there are no past papers questions strictly related to this 1.1.3, but this is the knowledge that you need to show to solve some other more complex questions. Okay, so it doesn't mean that this topic is not very important because it's not in a question like it is the topic, but the knowledge that you acquire by understanding this will be useful to approach and solve questions, more complex questions from paper two, for example, on paper one even. Okay, so the first one is this one. I want you to try, stop the video, and then you will check if you got the correct answer. Okay, so it says, at which point in a heating curve does the temperature remain constant while a substance absorbs energy? Keywords here, which point at the heating curve. So we need to go to the heating curve. Does the temperature remain constant while substance absorbs energy? So the key terms here will be temperature remain constant. Here we have the curve, the heating curve, the change from solid liquid gas, everything that we have explained and talked before. So it says when the gas is heated under pressure, so the gas is heated under pressure. In that case, they are talking about E and F. So meaning that probably that won't be the option. Then we have during boiling, when inner particle forces are broken. Okay, when boiling, so this is the boiling, the temperature remain constant. Okay, the temperature remain constant because it's not changing here. So that's a correct answer. We could say that this is correct. Let's highlight it in green, but sometimes we have some two correct. And then we need to pick the more suitable for the question. So see, here we have when the solid is being heated below its melting point. So solid is heating below its melting point. So it makes no sense, this option. So, and then we have when the gas particles gain kinetic energy. When the gas particles gain kinetic energy, the temperature is increasing. So meaning that the answer would be B during that process. Okay. Now, I want you to try the second question. First, read the question, stop the video, try to do it by yourself, and then we play the video and we see the solution. Why does boiling require more energy than melting? And this is something that if you watch the complete video, you will understand why this line in B and C is shorter than the D and E. So that will be very easy for you to answer if you watch the video completely, okay? It says it occurs at higher temperature. Because it occurs at higher temperature, that's the reason? I don't think that's the reason for the difference in energy. It involves breaking some hydrogen bonds. So we are breaking hydrogen bonds when boiling. Why does boiling require more energy? Here we have boiling. We are breaking hydrogen bonds. Intermolecular forces. Okay, this could be good. But it says only. Mm, there could be more intermolecular forces. Let's see the other answers. So we have it requires breaking all the interparticle forces. It requires breaking all interparticle forces. Maybe all interparticle forces is better than hydrogen bonds only. Some structures like CH4, some structures uh, that are not doing hydrogen bond, they are doing van der Waals forces, meaning that we have dipole-dipole attractions or dipole-induced dipole forces, meaning that the interparticle forces. So this is the more accurate, this is the correct answer, we could say, from now. And it requires cooling before heating. No, I don't think this is not the answer. So the answer will be C. It's breaking all the intermolecular forces. Remember that in this point is shorter and is only breaking the bonds in the solid to make it liquid. It's breaking the structure, the lattice structure. Here we have exercise 3. What happens to the kinetic energy and temperature of a gas when it's heated under constant pressure? This is something that we discussed after explaining the change from Kelvin to Celsius. Kinetic energy and temperature. What happens to the kinetic energy and temperature? They will increase, they are attached, they are together, of a gas when it's heated under a constant. So here we have kinetic energy increases but temperature decreases. I think that is not possible because they go together. If one increases, the other one increases. It's not the other way around. Kinetic energy remain constant, but temperature increases. This is not possible because I mentioned before they walk together. So this is not possible. Both kinetic energy and temperature increase. Oh yes, this is our conclusion, our main understanding about this kinetic energy and temperatures. Here we have both kinetic energy and temperature increase. Yes, this is the correct answer, but let's read the last one. Both kinetic energy and temperature decrease. No, this is not possible because we are heating up. So increasing, we are increasing the energy. We are heating up. So if we are heating, we are adding energy. We are not decreasing. We are not decreasing energy. So that's why the temperature is increasing and the kinetic energy. Number 4, which of the following statements about temperature is correct? So it says, the Kelvin scale is unrelated to kinetic energy. Well, that's false. That is totally false because the kinetic energy is temperature, and temperature is telling me, Kelvin is a scale that is telling me the kinetic energy. Absolute zero corresponds to maximum particle motion. No, it's the opposite. So when we have absolute zero is when the particles are not moving at all, and it's the only point. A temperature increase of 1 Celsius equals increase of 2 Kelvin? No, this is wrong. Remember that we said that an increase of 1 in Kelvin is an increase of 1 in Celsius. So the answer should be the last one. Let's see. Absolute temperature in Kelvin is directly proportional to the average kinetic energy of the particles. This is correct and is the summary of our today's lesson, and this is the most important bit. Okay, so please keep this statement as an statement. Now this one. Yeah, here we have the scale. Okay, it was a 4. Okay, now here we have exercise 5. Which of the following correctly describes the change in particle energy at the boiling point? Okay, boiling point of a liquid. Remember that in the boiling point of the liquid, the temperature is not changing, but the input energy is spent to break intermolecular forces, right? Okay, let's see. The average kinetic energy of the particles increased while the temperature remained constant. That's false. Remember that kinetic energy and temperature are working together. They are working together all the time. So this is not possible here. Here we have the potential energy of the particles increases. Potential energy, that's key, that's important. Please keep this in mind. Potential energy, not kinetic energy, but what the molecules are doing is the potential energy. So, of the particles increasing while temperature remains constant. The correct answer. Here we have both kinetic and potential energy increase as temperature increases. Yes, kinetic energy increases and temperature increases, but the potential energy is not increasing in this case. Or kinetic or potential, meaning that is related to the energy. And here we have that the particles lose potential energy as interparticle forces are broken. So they are not losing potential energy. So the potential energy is there, and the potential energy is the one that is allowing the breaking of these interparticle forces. Okay, so we'd say that the correct answer for this question is this one. The potential energy of the particle increases while the temperature remains constant. Okay, here we have these questions. Remember that I am taking some questions and some resources from this International Baccalaureate Organization book, and so, from another IP resource. Okay, guys? So this is the end of this video. I hope you enjoyed. I hope you learned. If you have questions, please in the comments, and don't forget to like and have a good one.